Okay, so welcome to topic 6, redox reactions and solubility. Now, in today's topic, we're going to be talking firstly about precipitation reactions and general solubility problems, and then we'll go into redox reactions. And the actual example of a redox reaction is in a separate file. Okay, so the types of reactions in aqueous solutions. So reactions of inorganic compounds can be classified into four main types. You have your precipitation reactions, and this is when you have an electrostatic attraction between cations and anions and you get an ionic lattice formed. We have redox reactions. We have the transfer of one or more electrons from the reducing agent to the oxidizing agent, okay, and that gives out a different product or molecule from that transfer of electrons. We also have acid-base, which we've talked about in the previous topic, and this is the transfer of a proton from an acid to a base. And we have complexation, and this is with our transition metals, which we'll talk more about in our next subject that goes on from this one, biological and physical chemistry. So the competition that occurs between the species in the reaction is different for these different types of reactions. So for precipitation reactions, we've got cations and anions, and the driving force is the insolubility of the salt that's being formed. Redox, we have electrons being transferred, and the reduction potential of the species is the driving force, so how likely is that species to give up or accept electrons. So acid-base reactions are similar, but they're talking about protons now. So it's how strong that acid is or how strong that base is, and how likely is a proton transfer to occur. Okay, and so remember there's those weak and strong acids and bases. So your strong acid completely ionizes in water, and your weak acid or base partially ionizes. So they're weak electrolytes. And we have our complexation reactions, which is when you have transition metals and ligands that are coordinated to the transition metal, and the stability of the complex that's formed is the driving force of these ones. Okay, so just back to hydrogen bonding and water again. So remember, water is a bent molecule. Okay, so we have that downwards of those hydrogens, and they're delta positive. Okay, and we've got the oxygen, which is in a bent conformation above the hydrogens, which is your delta negative. So remember, delta negative means it's more electronegative in comparison to these hydrogens. So the electrons will exist more likely on that oxygen, and the electrons we're talking about are those two electrons that are in that proton oxygen or hydrogen-oxygen bond here. So we can put a dipole moment across that bond to indicate where those electrons will be sitting. Okay, like we've talked about, there's special properties of water because of this polar nature, and that's the high boiling point. So remember, there's lots of hydrogen bonding interactions that need to be broken for the compound to go from a liquid into a gas state, and it has a high heat capacity. So the water can absorb a lot of energy before it actually changes its temperature by a degree. So non-covalent forces called hydrogen bonds are what makes this happen, okay? And this is when we have an electronegative oxygen that's bonded to an electropositive hydrogen, and that electropositive hydrogen, because it's electropositive now, has a weak coordination to another electronegative oxygen, okay? So the hydrogen bond involves three atoms. There's a covalent bond, and then there's a weak hydrogen bond interaction, which is that dashed line that we usually see. So something that is a hydrogen bond donor is an electronegative atom that has a hydrogen attached, and something that is a hydrogen bond acceptor is another electronegative atom. Okay? So depending on how the molecules interact, one species might be a donor and the other one an acceptor, but you might have the reverse also being possible. So you can see here we have a hydrogen bond donor is the water, and the NH3 is a hydrogen bond acceptor, the nitrogen there. But the hydrogen bond acceptor can also act as a donor to another water molecule. So depending on the environment that it happens to be in, they can switch between being an acceptor or a donor. Okay, so water soluble and fat soluble. So all charged species, so anything with a positive or negative charge, so your atoms or ions, dissolve in water. Okay, and this is where we have that hydration sphere that we've talked about before. So remember, you've got your negative anion, and then you have your positive side of the water molecule interacting with that negative charge, and we get a sphere. So all the water molecules totally surround that negative charge. Okay, we also have the same thing happening with positive ions or positive atoms, and this is when we have the electronegative oxygen coordinating to that positive charge. So we have the opposite charges attracting, and the water molecules surround that particular atom or ion, and it can get pulled away from the ionic lattice. Okay, so that's how solubility works with these charged species, and it's energetically favorable to form that hydration sphere or shell. So for ionic solids, the driving force for dissolving depends on how strong the electrostatic interaction is between the cations and anions, and how well the ion dipole force is with the water. So ion dipole force is when we've got an ionic compound or ionic species like a Na plus, for example, and we have the dipole force. So we have a molecule that has a dipole across it. And remember, we talked about the dipole on the water. So the dipole is going across that water molecule, and that's what makes it a polar compound. So substances will dissolve in water to varying degrees, and it depends on how polar that molecule is and how many hydrogen bonds can be formed between that particular molecule and water. So the sorts of things that make something polar is electronegative atoms. So you can look at the ratio, if you want, of oxygens, nitrogens, sulfurs, chlorines in the particular compound and compare them to your non-electronegative atoms such as carbon and hydrogen. And the more electronegative atoms that you have for every non-electronegative atoms, you could say generally the more polar it would be. So we've got some examples of this in our tutorial sheet that we'll work through. So the reason electronegative atoms make something polar is because we have a dipole and across the molecule, and then the electronegative atom can hydrogen bond with a hydrogen that's bonded to a water molecule. Okay, so that's the hydrogen bonding interaction, again making it that polar. Non-polar, on the other hand, things that do not contain electronegative atoms, so it's mainly just carbons and hydrogens, and these non-polar compounds do not dissolve in water. Okay, so an example here is a non-polar solvent, which is hexane, and we've got a non-polar compound which is an oil here, and these two would dissolve together, okay, but neither one of them would dissolve in water. And they won't dissolve in water because there's no hydrogen bond interactions that can occur, okay, because there's no electronegative atoms. So the longer the chain, the more non-polar it is, and the shorter the chain, the less non-polar it is, okay. And the general rule is like dissolves like. So polar molecules dissolve in polar solvents, and non-polar molecules dissolve in non-polar solvents. Okay, so remember to work out if it's polar or not. Now we don't need to think of the shape of the molecule, we just need to think of the ratio of electronegative atoms to non-electronegative atoms. So remember, electronegatives, oxygen, nitrogen, sulfurs, and your halogens, and your non-electronegative are generally just your carbons and your hydrogens. Okay, so this brings us into our lipid membranes. So an example of a lipid is this cis-9-hexadecanoic acid, okay, and it's got a 16 carbon chain, and there's one double bond in it, and that double bond is occurring at carbon number 9. So this particular lipid is a monounsaturated lipid, or an omega-7. So monounsaturated says that there's one unsaturated bond, okay? And an unsaturated bond is a bond that does not have the maximum amount of hydrogens that it can possibly have. So a bond that does have the maximum number of hydrogens it possibly can have is a single bond. So an unsaturated bond is a double or a triple. So there's a double bond in this molecule, and omega-7 is saying it's the 7th carbon from the tail end. Okay, so 1, 2, 3, 4, 5, 6, 7th carbon. So omega-7. So this particular lipid has a hydrophilic polar head. So it's a carboxylic acid at the top, and that's the polar head, and it's got a hydrophobic non-polar tail. So the different parts of this molecule will act differently in different environments. So the polar head group will like to be in a polar environment, okay? So it would like to be close to water, and the non-polar side would be in a non-polar environment. So it needs to be excluding water for it to be happy. So how do these molecules do that? So we can get micelles forming, we can get bilayers, or we can get vesicles forming. So you can see the blue dots is the polar head, and the yellow squiggly line is that hydrophobic tail. So if we're in water and we've got a really small droplet of this lipid, we might get micelles forming. So we have all the polar head groups on the outside, and all the hydrophobic tails tucked really tightly in together so that they're excluding that water, and we get a little lipid droplet. Okay, so these are very, very small droplets at that kind of level. You can get bilayers, which we get in our membranes. Okay, so our membranes are lipid bilayers, so you've got your polar heads on the outside, and you have one sheet at the top and one sheet at the bottom, if you want to think of it like that, and you have the non-polar tails in the middle. And when your lipid structures get bigger, you can get things like vesicles, okay? And that's when you've got the polar in the middle and the polar on the outside. So it's kind of like a bilayer that's been closed back on itself. Okay, so these fatty acids can be stored as triglycerides. So this is what a triglycerol structure looks like. So we have a linking CH2 unit here that makes an ester bond, and then we have our lipid hydrophobic non-polar tails out here. Okay, so it's just the way that we store fatty acids, and then when they're needed, then we take them off the triglyceride and make them free. Okay, so membranes are comprised of phospholipids, okay, glycolipids, and ether lipids and triglycerols. So triacylglycerols. So here you can see is a membrane. You can see you've got your polar head groups on the outside surface, you've got your non-polar tails in the middle, okay, and you've actually got different little things embedded in your membrane, and the way they embed in the membrane depends on what is on the outside of that particular thing and what is the nature of it. So for example, if you have an integral protein like this one here, this big one, this part of the protein would be non-polar to interact with the non-polar region, and this part on the outside here and here would be bent so that the polar parts would be exposed to the water environment that's inside or outside the cell. Okay, so any of the non-polar residues in here will be tucked into the loop section. Okay, so you've got your sterols, okay, so they're quite non-polar, fitting into the bilayer there. And you've got your glycolipids and your oligosaccharides, okay, so you've got your sugar chains. And your sugar chains, sugars are very polar. We know sugar dissolves in water, and if we actually have a look at the structure of a sugar or a carbohydrate molecule, it's a very polar molecule, and again we'll look into these structures in the next chemistry subject. So basically what we can take away from this lipid membrane structure is that the non-polar regions are in between the bilayer with the hydrophobic tails of the lipids, and the polar ones are on the outside. So if you've got a channel going through it, the channel would be non-polar, okay? And then the inside of the channel would be polar, so you can get the charged species going through if you've got an ion channel, for example. Okay, so let's have a talk about precipitation reactions. So precipitation reactions we're going to be doing in our last lab. So what we're going to get is we're going to get two different ionic solutions and mix them together. And when we have, so ionic solutions you can think of as salts, okay, so like sodium chloride, and we might have potassium iodine or something like that, and if we mix them together we have a combination of the cations and anions in solution, and they swap their partners, and then depending on their solubility we might get a precipitation that occurs. Okay, so what do we have on this slide? Here we have, if one combination of the cation and anion corresponds to an insoluble salt, then this salt will precipitate. And how do we know if we're going to get an insoluble salt? We look at our rules, and that's on your extra sheet that you will be getting in your exam. Okay, and this solubility itself is a physical property of a pure substance, and the precipitation reactions and whether or not something will occur is what we need to predict, and we've got these tables to tell us this. These solubility rules have been adapted over years of observations, and the strategy for solving these problems is, firstly you decide which ions will be in solutions, you cross over, see what combinations you can get, and then you look up your solubility chart and you see, okay, now this is a possible combination, will that be soluble? Won't it be soluble? Okay, so step 1, write out what the ions are in solution. Step 2, change partners, so you cross them over. Step 3 is write the balanced equation. Step 4 is check the solubility rules for precipitation. And step 5 is write the equation in the correct form. Okay, so if something is soluble, we write AQ in subscript next to that particular complex. If it makes a precipitation or a solid that forms, if it's partially or marginally soluble, we still have something that's going to precipitate out, so we need to put a little subscript S for solid, indicating that there's that precipitation occurring. So our solubility rules. Most nitrates, so NO3 minus, are soluble. This one's really, really key to remembering. If you see a nitrate, it's going to be soluble. There's no point in looking it up. It makes it a lot quicker if you remember that rule. So most ionic compounds of alkali metal ions, so that's your lithium, sodium, potassium, cesium, rubidium, and NH4 plus are soluble. Most chlorides, bromides, and iodides are soluble, except if you have a combination of one of those with silver, lead, or mercury. Okay, so if you have a combination of one of those with silver, lead, or mercury, you will get a precipitation occurring, so you would write a little solid subscript next to it. So most sulfates are soluble, and your exceptions are barium, lead, mercury, and calcium. So if you have a sulfate with one of those ones, it forms a solid. So most hydroxides are slightly soluble. So pretty much most hydroxides will form a solid, a precipitation, except if you have potassium and sodium. They're highly soluble, so you don't get a precipitation occurring. Barium, strontium, calcium are marginally soluble, so you get a little bit solubilizing, but most of it is not solubilized. So for those examples there, you would write a solid. So most sulfides, carbonates, chromates, and phosphates are only slightly soluble. Okay, so if you get any one of those, you would write a solid next to it. So let's have a look at an example. Okay, so we've got 3 different ways of writing out our equations. We can write our formula equation, our complete ionic equation, or our net ionic equation. So what is the difference? The formula equation is the formulas of the ionic compounds. So what are you starting with? You've got K2CrO4, we've got barium nitrate, and we're going to BaCrO4, and then we've got 2 potassium nitrates. Okay, and we've indicated that these 2 starting ones are soluble. The barium chromate, I think it is a solid, and we've got our potassium nitrate is soluble, because all nitrates are soluble. So our formula equation shows you the complete ionic structures. Complete ionic equations show you the ion species, okay, that make up that particular formula equation. So we're splitting each of those into their ionic components. So for K2CrO4, we've got CrO4 minus, 2 minus, sorry, and 2K plus. So when we split it, we don't leave it as K2 subscript. We put the 2 out the front because now our particular ion is K plus, and we've got 2 of them that are in solution, so we need to put the balancing out the front. So now we've got the coefficient out the front. So we've got 2K plus, we've got our CrO4 2 minus, we've got Ba2 plus, and we've got 2 nitrates. So we've got the 2 out the front, and we've got NO3 minus. So we leave our solid that's formed as a solid, and then we have our other 2 species. So when you look at your complete ionic equations, you can see that there are what we call spectator ions. There are ions that are on the left and the right hand side that are not changing. Okay, so that's your potassium and your nitrates. What we can do is eliminate these from our equation, and we would therefore get our net ionic equation. Okay, so this is just showing you what is combining to give you your barium chromate solid. Okay, so this is a practice problem, and we'll go through this one in the lecture. I might put up an extra video, see how we go for time. Okay, and next we have our redox reactions, and I'll do a different video for you on that one. Okay, so I hope this helps. Thank you.